Hello everyone, welcome back to our discussion on organic chemistry, the basic concepts. In this part, we will see hyperconjugation. Hyperconjugation, by definition, is the interaction of electrons in a sigma bond with an adjacent p orbital, which is either empty or partially filled, and it gives or it results in the extension of the CH or the sigma molecular orbital to increase the stability of the system. Before going to the details, let's see some important features that it is a permanent effect, that is hyperconjugation occurs in a molecule in its structure intrinsically without the requirement of any additional condition or external condition such as the presence of a reagent or so. And it involves delocalization or movement of sigma electrons to p orbitals, and mainly the carbon-hydrogen sigma bonds are delocalized in hyperconjugation. Before seeing the hyperconjugation effect in detail, let's see what is conjugation. Conjugation involves delocalization of pi electrons. Like in this case, here is a beta carotene molecule. Here you can see pi electron clouds are placed on every carbon on the long chain, and here the pi electron clouds, due to their spatial occurrence, they can be delocalized like this from one position to another position, resulting in charge separation on two ends of the molecule. This is a typical conjugation involving pi electrons, that is, pi electrons are delocalized from one atom to the other atom. On the other hand, hyperconjugation is a higher degree of conjugation, or it's a special case of conjugation involving sigma electrons. Like in case of ethyl carbocation, as a carbocation bears positive charge on the carbon atom. Here, ethyl carbocation has got two carbons, one is sp3 hybrid and the other is sp2 hybrid carbon, and the charge is present on this sp2 hybrid carbon. So let's represent this CH, one of the CH bonds on sp3 hybrid carbon with the orbitals involved. Here you can see the sp3 hybrid orbital of the carbon overlaps linearly with the 1s orbital of the hydrogen atom to form this CH bond. And the second carbon, the sp2 hybrid carbon, has got an unhybrid p orbital which is empty, and this p orbital lies in the perpendicular plane to the hybrid orbitals forming the other two carbon-hydrogen bonds. And electrons involved in the CH bond can now be delocalized or moved to the neighboring unhybrid p orbital which is empty like this, because they are lying in the same plane now. So this delocalization of electron, the sigma electrons involved in the CH bond, is called hyperconjugation. And the consequence of hyperconjugation is like this: the CH bond is now partly moved to the carbon in between the carbons. Therefore, the carbon-carbon bond is now enhanced or enriched to form a double bond like bond, and the charge now moves on this hydrogen because the hydrogen now lost its electron, not completely but somehow partly the hydrogen is losing its bond pair of electron towards the carbon. That is why in the end the structure will look like so. The structure shown over here, this is the no bond resonance structure. This is called a no bond resonance structure because the bond between carbon and hydrogen, or the electrons involved in this bond, are now moving on to the p orbital of the neighboring carbon atom. And hydrogen feels that there is no electron in between that hydrogen and carbon. That's why hyperconjugation is called no bond resonance. So there is a resonance, the structure is resonating between in this no bond form and the typical or previous form. Hyperconjugation occurs mainly in alkenes, carbocations and free radical, and the important criterion is that the species should have alpha hydrogen so that hyperconjugation is occurring. Alkenes like this, here this one shown here is an alpha hydrogen, and this alpha hydrogen, the electrons involved in this carbon hydrogen bond can be mobilized to the carbon having this unsaturation. Like this, carbocations also can have hyperconjugation provided they have good alpha hydrogen, also free radicals. And one important feature of hyperconjugation is that the more the number of alpha hydrogens, the more will be the no-bond resonance structures or hyperconjugated structures, and therefore this will contribute to the higher stability of the structure. The first structure has got 3 alpha hydrogens, that is hydrogen placed on the alpha carbon to the carbon bearing the charge, and the second structure has got on the other hand only 1 alpha hydrogen because the other 2 positions are substituted by R group. Okay, so the second structure has got only 1 alpha hydrogen, whereas the first structure has got 3 alpha hydrogens. So the first structure can have 3 no bond resonance structures, and that is why the structure 1 is more stabilized than the second structure. And now coming to these two species, the structures 3 and 4, if you compare, you can see the carbocation here in the third structure is stabilized because there are 3 alpha hydrogens, therefore 3 no bond resonance structures you can have. On the other hand, in the fourth structure, you have more alpha hydrogens like 3 here and 3 on each methyl group like this. So there are 9 alpha hydrogens on the structure 4. Therefore, that particular carbocation is more stabilized than the structure 3. So this way, you can increase the stability of the carbocation by introducing more alpha hydrogens or substituting with more methyl group, let's say. And the idea of hyperconjugation is used to explain relative stability of similar chemical species. Here you've got 1 butene in the first structure and 2 butene in the second structure. 1 butene has got 2 alpha hydrogens like this, whereas the 2 butene has 6 alpha hydrogens. Therefore, 2 butene is more stabilized. It has got more no bond resonance structures. Therefore, it is more stabilized than 1 butene. Likewise, stability of carbocations can also be explained based on hyperconjugation. You've got primary and secondary carbocations here. The first structure is the primary carbocation. It has got 3 alpha hydrogens, whereas the secondary carbocation has got 6 alpha hydrogens here. Therefore, the secondary carbocation, which is possessing more no bond resonance structures or hyperconjugated structures, is more stable than the primary one. In this way, you can explain the relative stability or higher stability of tertiary carbocation with respect to that of secondary carbocation. Okay, this is all about hyperconjugation, the introduction, the idea what is hyperconjugation, why it is called no bond resonance, and how to use the idea of hyperconjugation to explain stability of species. With that, we close this session, and in the next session we will see reaction intermediates, that are carbocations, carbanions and free radicals. And thank you.